Hello everyone and welcome back to our science podcast series. I'm Eric and today we are diving into the fascinating world of chemical bonding and molecular structure, the very principles that explain how atoms come together to form the endless variety of substances we see around us. If our last episode explored how quantum mechanics explain the structure of atom, today we are taking the next step, understanding how those atoms interact, connect, and create everything from the air we breathe to the DNA inside our cells. To begin, let's revisit why atoms form bonds in the first place. Every atom seeks stabilities, and the most stable configurations is one where its outermost energy level, or valence shell, is full. The idea, known as the octet rule, drives most chemical bonding. Noble gases like helium and neon already have complete valence shells, which is why they rarely react. However, most other elements don't. So they gain, lose, or share electrons to reach their stable configurations, forming chemical bonds in the process. One of the most basic steps of bonding is ionic bonding. This occurs when one atom donates an electron to another, forming charged ions that attract each other. For example, sodium and chlorine from sodium chloride or table salts. Sodium loses an electron to become a positively charged anode, while chlorine gains one, become negatively charged. The electrostatic attraction between these oppositely charged ions hold the compound together. Ionic compounds generally form crystalline, solid, have high melting points, and conduct electricity when dissolved in water. Then comes covalent bonding, where atoms share electrons instead of transforming them. This type of bond is common in molecules like water H2O and oxygen gas O2. In a water molecule, for instance, each hydrogen atom shares an electron with oxygen, helping all three atoms achieve stable configurations. Depending on how equally electrons are shared, covalent bonds can be non-polar or polar. In polar covalent bonds, one atoms attract the shared electrons more strongly, creating partial positive and negative charges within the molecule. This is why water molecules have a bent shapes and exhibit properties like surface tensions and hydrogen bonding, unique characteristics that make water essential for life. Metallic bonding, on the other hand, is that what gives metals their distinct properties like conductivities, malleabilities, and luster. In metals, atoms don't hold onto their valence electrons tightly. Instead, these electrons move freely throughout the sea of electrons, allowing metals to conduct heat and electricity efficiently and without breaking. This electron's mobility also explains why metals shine. When light hits them, the free electrons reflect it easily. Now let's explore how quantum theories help us understand molecule structures more deeply. The quantum mechanical model explains that electrons occupy orbitals, regions where they are most likely to be found. When atoms form covalent bonds, these orbitals overlap. Depending on the type of overlap, we get different bond types, sigma and pi bonds. Sigma bonds occur when orbitals overlap directly between atomic nuclei, while pi bond results from the side-by-side overlap of p orbitals. These concepts explain why double and triple bonds, which include both sigma and pi bonds, are shorter and stronger than single bonds. Molecular geometry, or the shape of molecules, is another fascinating aspect influenced by quantum theory. According to the VSEPR valence shell electron pair repulsion theories, electrons pairs around the central atom repel each other and arrange themselves as far apart as possible. This determines whether a molecule is linear, bends, trigonal, planars, or takes on another shape entirely. For example, carbon dioxide is linear because there are no lone pairs on the central carbon atoms, while water is bent due to the repulsions between the two lone pairs on oxygen. The polarity of a molecule which affects its solubility, boiling points, and reactivity also depends on both the type of bond and the shape of the molecule. Even if a molecule has polar bonds, it can still be nonpolar overall if the shape causes the bond dipoles to cancel out, as in the case of carbon dioxide. In contrast, water bent shapes ensures that its bond dipoles don't cancel, making it a highly polar molecule. Hybridization is another concept that connects atomic orbitals and molecular geometry. It describes how atomic orbitals mix to form new hybrid orbitals during bonding. For example, in methane, carbon's 2s and 2p's orbitals combine to form 4 equivalent sp3 hybrid orbitals. Explain why the molecule is tetrahedrid with equal bond angles. Similarity, sp2 and sp hybridizations explain the geometries of molecules like ethane and ethane. Finally, the concept of intermolecular forces explain how molecules interact with each other. These forces, which include London dispersion forces, dipole-dipole interactions, and hydrogen bonding, are much weaker than chemical bonds but crucial for determining physical properties. They explain why ice floats on water, while oil doesn't mix with water, and why different substances boil or melt at different temperatures. In a sense, chemical bonding and molecular structures are the bridge between the microscopic world of quantum mechanics and the macroscopic world we experience daily. They explain how the invisible interaction between electrons give rise to the tangible matter that shapes our universe. That's it for today's episode on chemical bonding and molecular structure. From the transform of electrons in ionic compounds to the shared electron clouds of covalent molecules, we have uncovered how atoms unite to form everything we know. Stay tuned for our next episode, where we will explore chemical reactions, the dynamic process that transform substances and power the world around us.